All right, 3.2 trends in groups. But before we get started, let's take a quick recap. Now, 3.1 was all about classifying the elements of the periodic table. So we had multiple methods. Actually, we took care of three methods in this portion. The first one was that we divided the whole periodic table into groups and periods. We gave them numbers and names, and then we were able to talk about them in different manners. You have a colored periodic table here, and you know that how to take care of groups and periods, how to talk about them, how to take data out of the periodic table for your own good. Then the next form of classification was metal and non-metals. There was a proper staircase in the periodic table. The whole left side was a big, huge set of metals, and a little extreme right-hand side was the whole accumulate of non-metals. Hydrogen is also a non-metal that is present on the top of the periodic table and has a unique position, which we're going to discuss later in the other part of the chapter. Now, we had a huge table for metals and non-metals, defining them and talking about all the exceptions there are in this table. We also defined metals and semi-metals at the bottom of the same page, page number 57. And we discussed that electrical conductivity is the most probable test that you're going to go with if you are going to distinguish between a metal and a non-metal for any unknown elements. We move on, we discuss about the groups and periods, and we tell you that all the elements are commonly known as main group elements. However, the center of periodic table is known as transition element. We haven't discussed the center of the periodic table yet, but we'll do that a little later in the same part of the book. Now, moving on, electron arrangement was a very important part of the periodic table. It seems that the whole periodic table is properly arranged as per the electron arrangement, so much so that every group number for main group elements is representing the number of electrons in the outermost shell of the elements that lie in the same group. So this becomes pretty easy. Group number is equal to the number of outermost shell electrons, but there were a couple of exceptions. Hydrogen and helium were those exceptions, and also that we called group 8 as group 0 and not group 8. There is a very good reason coming up in the part we are supposed to study today, why we call it group 0 and why not group 8. Lastly, the period numbers were given in such a way that they tell you how many shells of electrons the atom has. So the digits in the electronic configuration, the total number of digits actually represented the number of shells, which in turn represented the period number. And the last digit on your right actually represented the group number or the number of electrons in the outermost shell. Now this made everything easy for us. We have a quick little tip over here that all the numbers in the electronic configuration, if you add them up, you get a number which is known as Z. That's the atomic number of a specific element. And from there on onwards, you can identify the elements and solve the question. Now, general trends of the periodic table, if we leave aside the noble gases, group 8 or group 0, there were some specific general trends. We discussed densities, melting points, boiling points. We talked about atomic size. We talked about metallic character. We talked about reactivity. We discussed the most reactive metal in useful amounts, that was sodium, most reactive non-metal in the useful amounts, that was fluorine. And we discussed as a whole trend of the periodic table. Also, a couple of exceptions were also discussed at this part. Now, this was a quick recap, and now we're going to move on to 3.2 trends and groups. The fourth and last classification is actually discussed in this portion. What we're going to do is that we're going to discuss most important groups and periods in this portion, or the parts of periodic table in this portion. So as I stated earlier, we're going to talk about group 1 in here. We're going to talk about group 2. We're going to talk about group 7. We're going to talk about group 8, or what most probably is better to call group 0. And as a whole, we're going to discuss transition elements, which are the center of the periodic table. It's not just one group or one period. We're going to discuss the whole center of the periodic table as a whole as transition elements. So that's what we are about to do in parts of 3.2 and some parts of 3.3 included. To begin with, group 1. Group 1 are known as the alkali metals. Now, from this portion, from here on onwards, we're not going to just discuss the trends. Actually, if you're going to go ahead and if you're going to see the past 10 years papers from these portions, you will find that most of the discussion is about the properties of elements in group 1, the alkali metals. And those properties are actually bifurcated in two types. Number one, physical, and number two, chemical. Now, physical properties are all related to the appearance or the physicals of that specific element. How does it look like, whether it's hard or soft, what kind of melting or boiling points it has, what kind of density it has, any color, any odor, any shine. These are the physical properties. Malleability, ductility, electrical conductivity, thermal conductivity, these are all physical properties. To put it very easy about the chemical properties, anything that you can write in the form of a proper chemical equation is actually a chemical property. So reaction with another metal or non-metal, chemical property. Reaction with oxygen, chemical property. Reaction with air or water, chemical property. Reaction with acid or alkali, chemical property. Reaction with other metals or non-metals, or reaction with halogens, chemical property. So all of these comes as a part of chemical property. Remember, any discussion about reactivity is also chemical. Loss or gain of electron or sharing of electron is also chemical, because that's a part of chemical bonding. So that's how we can easily separate physical and chemical properties. Now, what I do for the sake of ease of children is that I talk about physical and chemical properties in such a way that this whole paragraph lists actually a lot of them. So what we're going to do is that first physical property will be marked as 1p, and then 2p, and then 3p. So if this whole paragraph has 3 or 4 physical properties, you can list them separately. And every chemical property is also marked as 1c, 2c, or 3c, so on and so forth. You'd have a couple of or 3 chemical properties of these. So whenever your past papers are going to ask you to list a couple of chemical properties or physical properties of any specific metal or any specific group, you'd know how to do. All right. So just as the sake for the easier answers, what we're going to do is that we're going to mark them properly. Every P stands for physical property. Numbering suggests that it's the first, second, or third physical property. Every C stands for chemical properties. The numbering again suggests the same thing, whether it's the first chemical property, second, or third. All right. If a chemical or physical property is repeated, we also repeat the number. So let's move on. The metals in the group 1 are often known as alkali metals. We call them by this name because whenever we use the word metals for a specific group or a period, that means all the set of elements are actually metals in there. The word alkali represents a literal meaning alkali, and actually whenever they react with water, they give us good alkalis, that's why. Hence the name alkali metals. Now, they are soft solid. This is the first physical property, so 1p. In fact, what I'm going to do is that I'm going to use a different color this time. So it's separable for you. So it's, my bad, it's 1p, first physical property. Low melting point, second physical property. Why do I keep writing C? Low densities, third physical property, 3p. Now, they are highly reactive and stored in oil to prevent them from reacting with oxygen and water. So if they react with oxygen, that's first chemical property. If they react with water vapor in the air, that's second chemical property. When freshly cut with a knife, and this means they are soft, cut with a knife means they are soft, all right? So cut with a knife, I'm going to mark that as 1p again. So we have already mentioned that they are soft solids. All of these metals have light gray silvery surface. So this is again, this is a shiny property. So we're going to mark it as fourth property, 4p. It quickly tarnishes, becomes dull because it reacts with oxygen in the air. So to be honest, this is tarnishing is First chemical property, reaction with O2 in air and losing luster. All right. So it loses its luster. We call it tarnishing. The word literally is tarnish. It means reaction of a metal or something with oxygen in the air probably and losing its shine, losing its colorful, shiny appearance. If not colorful, the shiny metallic shine-based appearance in this specific case. Reactivity increases as we go down the group. Now, this is a trend, which means the elements up in the group are more reactive, the elements at the bottom are less reactive, actually, and the elements at the bottom are more reactive. Sorry, the ones up, less reactive, the ones down, more reactive. All group 1 metals actually react with water. This is the same second chemical property. So 2C, they form hydrogen and they form an alkaline solution of a metal hydroxide. The reactions range from vigorous in case of lithium, and I'm going to simply scroll without erasing anything, to explosive in the case of cesium. Now remember, they just use the word vigorous for lithium, and they're using the term explosive in case of cesium. Now, here we actually end up with all physical and chemical properties, to be honest. They discuss francium at the bottom of group 1. It's very reactive, but since it's highly radioactive as well, it has a shorter half-life. I've discussed that in the previous lesson. Only 17 atoms of francium exist at any moment in time at the planet, and this is just an emission. So, of course, these are not useful amounts. So we do not discuss francium most of the time. And from here onwards, we actually drawing a boundary line for IGCSE chemistry that if an element is radioactive and is not found in a useful amount, we're not going to discuss that specific element all out of that group. Now, when I say that, and when you look at the periodic table, you'll find group 1 something like this. Now, the group starts with lithium on top, Li, then you have sodium, potassium, rubidium, cesium, and francium. Since francium is pretty rare, we're not going to discuss it, and we'll discuss the rest of the group. And this is what most of the questions in the past papers are about. But they might ask you to predict the properties of francium. Since you already know the trend, you can. For example, physical properties change down the group, the melting points become lower. So francium has the least melting point in all of these elements. Density become high, increases. So that's actually, this one was 2p, this one is 3p. They're continued in their trends. So yeah, there you go. You know that the francium density is highest in all the group members, but melting point is lowest in all the group members. You also know it's the softest of all of these members. You also know it's the most reactive of all of these members. So the alkali metals are most reactive metals that occur. They are known as alkali metals because they react vigorously with water to produce hydrogen and alkali solution. This is the reason for their name. Sometimes the question is about what do we call them, alkali metals? So the answer is as simple as that. All right.
Yes.
Okay. So what I'm gonna do is that I'm gonna clear this whole thing up. I'm gonna.
Yes, sir.
So now if we know how to bifurcate their physical and chemical properties, and we have also seen a chemical property of alkali metals reacting with water, what I'm going to do is that I'm going to jump to a specific part of the book where these parts are discussed again, in order to make sure that you also understand how to interlink the chapters. Not just that, you would know that you won't need to go through those parts of the book again. I'm going to specifically take you to the 8th chapter, since 8th chapter is all about metals, and you'd notice the same thing over there. Now, as soon as we start chapter number 8, which is patterns and periodic properties of metals, it literally starts with the alkali metals. They list the whole group. They talk about its properties. So you get to see that they are all reactive. They're stored under oil to stop them from reacting with oxygen or water vapor in the air, since they can react with both. They are soft and can be cut with a knife. Just give me a. So they are soft and can be cut with a knife. Whenever we're going to say or call an element as soft, where specifically when it's solid, it means we might be able to cut it with a knife. So at least this comes with a few alkali metals and a very few alkaline earth metals. Like all metals, they form positive ions by losing a single electron. They form compounds which have the similar formula. For example, all their carbonates have the same formula: Li2CO3, Na2CO3, K2CO3. The similarity in their formula actually go with carbonates, nitrates, hydroxides, you name it. Most of them form the same compounds. Now, they all react strongly and directly with nonmetals to form salts. Their salts are all white, crystalline, ionic solids that actually can dissolve in water. There are more physical and chemical properties over here. Now, the reactions of alkali metals with water, they have literally just written the reactions in their word equations and in their chemical equations. And when you see it, you would know that these are actually a repetition of letters. Here, good note. Now, this is 2Na reacting with two water molecules forming 2NaOH in H2. If this reaction was supposed to occur with lithium, simply replace Na with Li over here and Li over here. Literally, the rest of the equation remains the same. Or simply write lithium over here and lithium over here, and literally all other parts of the equation or names stay the same. It's so easy. If it's potassium, do the same. If it's rubidium, if it's cesium, does not matter. You simply need to repeat the same. And every time they're going to wind up like this. A metal reacts with the water, it forms a metal hydroxide and it forms hydrogen. All right?
Yes, sir.
Great. Now, not just this, chapter number 8 discusses the reactions with water, and they actually use different words. Take a look. Lithium reacts steadily, sodium reacts strongly, potassium reacts violently, rubidium reacts vigorously, and cesium reacts explosively. It must be written somewhere here. But okay, since it's not written, so we react vigorously for RB and we react explosively for rubidium. Why do we write it like this? You've already seen in the video that the utensils, be it a bathtub, be it a simple water tub, that they do not usually break with lithium, sodium, potassium. But as soon as we start using rubidium, you can rewatch the video on YouTube, you'd get to see that rubidium, cesium successfully breaks the utensils in which the experiment is carried on, right? That's an increase of reactivity right there. And you also know that you need to use different adjectives and a strong adjective as soon as you move from top to bottom in a group. Every time with every step, try to go with a stronger adjective. So from steadily to strongly, from strongly to violently, from violently to vigorously or explosively. You can even use the word explosively for both rubidium and cesium. Reaction with air, I told you their shiny metallic surfaces tarnishes to give you a dull layer of oxide. So the same thing happens here, here, and here. But slowly with lithium, quickly with potassium, sodium, very quickly with potassium, and you can write even quicker for rubidium and cesium than it does for potassium. So you can always write comparative lines. Not just that, the ions actually give specific flame colors. So whenever you put lithium ions in flame, the flame is going to turn red. For sodium, it is going to turn yellow. For potassium, it is still going to turn lilac. Lilac actually is close to purple, but I always ask my students to go with the exact color and not write purple. Purple is just there for your understanding, so you would know what lilac looks like, right?
Yes, sir.
Good, great. So this part of chapter end and in that part of chapter 3, you'd see that they match one another and they have shown you a lot of similar stuff, right? So I'm gonna continue with the same thing, but actually let's go back and forth. If I simply continue with the same thing, it's gonna be difficult for you to understand what I'm about to do. Now, take a look. This is group 1 alkali metals. As soon as it ends, the book starts with group 7, the halogens. The book does not take time to explain group 2, which is a part of IGCSE, and from which the questions are usually asked. Now, they did the same thing in chapter 8. So, for group 2, we're not going to study ID part from chapter 3, we're going to study it from chapter 8. So, I'm going to go a little bit forward and I'm going to take it out of chapter number 8. There you go. Group 2 metals is actually present on page 209 in chapter 8. Now, what's group 2? It starts with beryllium, then we have magnesium, calcium, strontium, barium, and radium. Again, radium is radioactive and is a rare element as well. So we're not going to discuss radium in detail, but yes, we're going to discuss from beryllium to barium in detail. These are known as alkaline earth metals. They show similar trends in reactivity as group 1, but they're less reactive than metals in group 1. They still take part in a wide range of reactions like the alkali compounds, alkali metal compounds of these metals. They also produce color characteristic flames. It's pretty easy. Magnesium does not give any flame color. Instead, it gives a bright, flashy white light. Magnesium has been a part of flashlights before we could come up with the digital method for flashlights. Previously, we used to burn magnesium, and magnesium ion used to give flash white light. So much so that in IGCSE chemistry, we do have an experiment of burning magnesium in air that actually produces a flashy white light. You can obviously go that with YouTube. You can search the reaction of magnesium in air on YouTube, or the CD that comes along with this book also consists of that video. All right. For calcium, the flame
Yes.
color is brick red. For strontium, it's scarlet. Scarlet is near to red, a mixture of red and orange. But it's better if you write scarlet and not write orange red, because those are slightly different things. Now, barium is apple green. I hope you understand apple green. Simply green and apple green are different. They have specifically used the color word apple green. Apart from the reactions given over here, I'm not going to go with reactions since that specifically is a part of chapter 8. I'm going to show you the colors. Take a look. The calcium is brick red, the strontium is scarlet, and barium is apple green. You might notice something carefully. The flame color originally was blue. The point you put this whole wire to take the flame test, from there on onwards, the color of the flame changes. The flame color is originally blue, you can see over here and here. But from there on onwards, the color of the flame literally changes as per the ion you put in it. The flame colors are just there for you to memorize, and usually that is a 1 mark question in any of the papers, be it paper 2, 4, or 6. So that's where we complete group 2. I'm going to get back to the similar chapter we were started at, and we're going to start discussing group number 7. So group 7, the halogens. We call group 7 as the halogens. The names that I've been taking since now, I am calling group 1 as alkali metals. I'm calling group 2 as alkaline earth metals. I'm calling group 7 as halogens. These are the common names of the entire set of elements that actually exist in here. Now, if you take a look at the periodic table, you're going to find group 7 something like this. It starts with fluorine, then we have chlorine, then we have bromine. Next up is iodine, and lastly is acetylene. Right? So we have 5 elements in there. There is one more element that is a part of the new periodic table, probably it's silverium or something. Fb, I guess, or maybe Fl, I'm not sure. But again, that's a part of the new periodic table, and very less amount of questions exist with that. There is probably only one question from 2020, but that's easier since you're supposed to predict the properties. As soon as you know the properties from here, it would be easier for you to predict those properties. Now, the most reactive nonmetals are halogens in the entire periodic table. In contrast with group 1, here reactivity decreases down the group. In group 1, the reactivity increases down the group. Since these are non-metals, the opposite, the reactivity decreases down the group. Fluorine is the most reactive non-metal on the planet. It's dangerously reactive. It's actually a pale yellow. It's a gas at room temperature. All right. There is a steady increase in melting and boiling points as we go down this group from fluorine to acetylene. And we're going to discuss some specific properties with the help of diagram. I'm going to erase some part of it. I'm not going to erase all of it. So you can see the group. Now, you already know from the lines right above this diagram that fluorine is pale yellow gas at room temperature. Take a look at chlorine. They say dense pale green gas. It's smelly and it is poisonous. You can skip the rest of the points. You only need to memorize first 2 points of each of these. All right. So first 2 points for chlorine, first 2 for bromine, and first 2 for iodine. Not need to memorize the rest. Okay. So the second point is actually the same for all of these. They're smelly, they're poisonous. The first point is different for all of these. This one is a pale green gas, a dense one at that. This one is a deep red liquid, and when it is converted into vapors, which it easily does, those are actually red-brown vapors. And in the case of iodine, my bad. Okay, in the case of iodine, I erased the wrong stuff. Okay, in case of iodine, it's a gray solid with purple vapors. Now, I hope you remember that we saw the diagram for purple vapors back in chapter number 2. So I'm quickly going to move over there. At the very start of chapter 2, we have the diagram, iodine. Iodine was an example of sublimation. Now, in this very test tube, you'll notice that at the bottom, we have this gray-black substance, which is actually converting into vapors with a dark purple color. So the solid has a different color as compared to the vapor, as you might can easily notice from this diagram. All right. So let's get back to the chapter.
Yes, sir.
So that's the colors right there. Remember, the colors of halogens is an easy part, but colors are an important part of IGCSE, and you are supposed to memorize all the colors. All right. Fluorine has been asked about in exam. It's given right on the top of this diagram. It's pale yellow. Fluorine, bromine, and iodine are already a part of this diagram. And as you go down the group, the color is actually darkening. The top ones are pale. The bottom one are a little bit dark. and the one at like iodine is getting darker. Can you predict the color of acetylene?
Of what, sir?
Of acetylene, the last element. Now, let me again repeat. Their colors were pale. This was slightly dark. This is more dark. Now you're supposed to predict the color of acetylene, the last element.
It
Look,
would be a color near to black.
great. Before I could make more set of hints, you have a perfectly good answer. So it would have a color near to black or dark black. Now, acetylene is highly radioactive, rare element. Most of the properties of acetylene are a mystery to human beings, but we can predict the properties. You've already predicted one of its properties, the color, the appearance. All right. So some common properties of halogens. They're all poisonous and they have a similar strong smell. Since they're all poisonous, so every time you are going to perform an experiment related to these, you will be asked to actually keep yourself safe and go for any safety measures if possible. Now, when I say it like that, these two are actually gases. This is the only liquid nonmetal on the periodic table, as I've said earlier, and these two are solids at room temperature. Okay. So when you're going to handle gases, make sure you're doing it in a fume cupboard, since they're very poisonous and it's clearly mentioned on the top of the properties before they mention anything else, right? If you're handling the liquid or the solid, make sure you have all kinds of safeties on. When you are working with them, it's better to work in a fume cupboard. If you don't have fume cupboard at school or in your lab, make sure it's a very well ventilated area. Make sure it's not a closed space. All right. Make sure it's not a closed space and it's very ventilated so that you do not inhale any of their vapors, since they're poisonous, since they can easily kill a human being. All right. So moving on.
Yes,
They're
sir.
all non-metals. They all form diatomic molecules. Since they exist in pairs, Cl2, Br2, I2, of course, F2, or if we talk about AT, it's going to form 82. So remember the same properties. Whichever property they ask you to predict for AT, of course, you can do it with like the rest of the group. For example, if all of them are non-metals, of course, AT would also be a non-metal. If all of them have strong smells, of course, AT is also going to have a strong smell. If all of them are poisonous, of course, AT is going to be poisonous too. In the similar way, if they exist as molecules made up of two atoms, diatomic molecules, AT is going to, of course, going to exist as 82, not 82, 82. All right, not like number 82. This is not
Yes,
what I'm saying. Yeah, let's not mix it up because I might sound like that. Okay, so they all have a valency or combining power of 1. So to form compounds with a similar formulae, for example, when they combine with hydrogen, all of them combine in the similar way. With chlorine and hydrogen, HCl. With bromine and hydrogen, HBr. With iodine and hydrogen, HI. What would be the formula of the compound that is formed from fluorine and hydrogen? Formula.
HCl.
Fluorine, not chlorine, beta. Fluorine. The symbol for fluorine is F, and that's at the top of this group.
HF.
HF. Great. Now, what if the same thing happens between hydrogen and acetylene? This time, you're not supposed to answer the formula, you're supposed to answer the name. So fluorine is converted into hydrogen fluoride, chlorine is converted into hydrogen chloride, bromine into hydrogen bromide, iodine into hydrogen iodide, so acetylene into what?
Hydrogen acid.
Hydrogen acetate. Remember, instead of writing I and E like fluorine, chlorine, bromine, iodine, we're actually replacing it with IDE, which is ide. So fluoride, chloride, bromide, iodide, and in a similar way, hydrogen acetate. Perfect. Now you know how you're going to predict the properties. Can you predict the properties?
Yes, sir.
That's great. If you can predict the properties, the question may come from any of these groups. It may be group 1, it may be group 2, it may be group 7, it may be group 0 or group 8. And they've already asked the question from, I guess, Liberium, that is at the bottom, that is even an element that comes after AT, astatine in the periodic table. So they might ask you to predict the properties. And if you know their properties, the properties of the rest of the group and what the trend is, you can, of course, predict it with the rest. For example, let's study the next point. Next point says their compounds with hydrogen are usually strong acids. When dissolved in water, hydrogen chloride becomes hydrochloric acid. When dissolved in water, hydrogen bromide becomes hydrobromic acid. And when dissolved in water, hydrogen iodide becomes hydroiodic acid. So this one formed HF. When dissolved in water, what would this be known as?
Um,
Look, hydrogen chloride is converted into hydrogen hydrochloric acid. It's not hydrogen, it's hydro now. It's not chloride, it's chloric. Bromide into bromic, iodide into iodic, so fluoride into
fluoride,
the whole name.
hydrofluoric
And where does the last word
acid.
come? Right, hydrofluoric acid. That's the perfect name. Now you know. So it's hydrochloric acid. Clear enough?
Yes, sir.
So what would this form? What would HAT or HAT form? Now this is a different hat from the hat that we usually call as a hat in English. This is a compound. So when dissolved in water, what would hat be known as? Don't say topi, because it's not that.
It will be hydroacetate acid.
Acetic acid. It's IC acid at the end. So it's hydro and acetic acid. All right,
Yes, sir.
great. Now, these are just predictions. You can always predict. They produce next point. They produce a series of compounds with other elements. So all compounds with chlorine are known as chlorides, with bromine are known as bromides, with iodines are known as iodides. So what would be the compound with chlorine known as?
Fluoride,
And what would be the compound of astatine known as?
acetate.
Perfect. Together, they're all known as halides. See, chlorine, chloride, bromine, bromide, iodine, iodide, fluorine, fluoride, astatine, acetate, but halogens, halide. Halide means we might be talking about fluoride, fluoride, bromide, iodide, or acetate. All right,
Yes, sir.
good. Let's continue predicting. The halogens themselves can react directly with metals to form metal halides, which means they can form metal fluorides or metal chlorides or metal bromides, so on and so forth. We simply called metal halides as salt, right? Which means
Yes.
sodium chloride the salt we eat every day, the white table salt, is actually a metal halide. That's why we simply call it a salt. Why? Because sodium is a metal and it's chloride, so it's a halide. Let's clarify with further points. And I'm gonna erase some of these parts. It's easier for us to move below. Now, they all form negative ions. They carry a single negative charge. For example, chloride ions are represented as Cl negative. Bromide ions are represented as Br negative. Iodide ions are represented as I negative. So what would be the fluoride ions represented as?
F negative.
Great. And astatine ion?
80 negative.
Wonderful. Now you know. Since you're predicting every answer correctly, so I hope you must be pretty confident about predictions, and this might be coming as a whole easy to you. Okay,
Yes, sir.
let's keep moving on. Now, there are gradual change in their properties as you go down the group. The boiling point increase, the melting point increase. Their state is changing from gas to liquid to solid. I've already explained it. The intensity of the color is also increasing. They're moving from pale to dark. So you would know that how the trend is going. As far as chemical reactivity, chemical processes are concerned. Now, I accidentally forgot how to mention these. Now, this is 1P, this is 2P, this is 1C, and this is 2C, the same thing. Again, a generic statement, actually that can be regarded as 3C, and that can be regarded as 4C. All right. Any of their colors and state of matter are physical properties. So if you mention chlorine as pale green, it would be another physical property. So now you know the physical and chemical properties from this big common properties table. All right. Can I clear it up?
Yes, sir.
So I'm going to clear this whole thing up. And let's move to the bottom. So chemical reactivity, chlorine and chlorine are extremely reactive. The rest of them may react easily. Usually with a metal, chlorine and chlorine burst into flames when they're placed in a jar of chlorine or fluorine. So metals actually burst. However, for aluminum, so for aluminum, heated aluminum, we pass over chlorine, the metal goes white and it forms like this, a metal chloride. This whole paragraph is actually talking about salt, how the salts are formed. So react a halogen with any metal on the periodic table, no matter which metal is that, be it a metal from group 1 or from group 2 or from group 3, maybe it is a transition metal, the resultant would be a salt. So aluminum also reacts strongly with bromine and iodine in the similar way. So of course, you can write the reaction that 2Al would react with 3Br2 to form in the presence of heat, and we write that heat above on the top of the arrow to AlBr3. Now you know you're simply supposed to replace the symbol of fluorine with the symbol of bromine or iodine in order to get your answers, right? Get the point?
Yes, sir.
Now the reaction given below, and I'm going to erase this huge part since this is getting a little bit difficult to see the whole thing with it. Okay, so moving on, this one below is about forming acid. How do we form acid? So hydrogen can react with any of the halogens in the similar way. Hydrogen reacts with chlorine to form hydrogen chloride gas. When this gas is actually dissolved in water, it forms HCl aqueous, which is known as hydrochloric acid. Remember, the gas is hydrogen chloride. The aqueous solution of it is hydrochloric acid. And this is G written in brackets. All right.
Yes, sir.
Good. This is an extension to the same reaction. I hope you may be able to write the same reaction as bromine or iodine. It would be H2 plus Br2 giving you 2 HBr. When you add water to it, it would become 2 HBr aqueous. So hydrogen bromide is a gas and hydrobromic acid is a solution. Both of these are explained in this area, right? Moving on, their reaction with water is known as the specific name, chlorine water or bromine water or iodine water. It's given a name like this, and this actually gives us a mixture of two acids. IC acid, hydrochloric acid, and OUS acid, hypochlorous acid. This hypochlorous acid is actually an oxidizing agent. We also call it a bleaching agent, thing that is written right under these lines. Bleaching agent is something that can bleach the colors. Anything that can convert a colored substance into a colorless substance is known as a bleaching agent. We commonly use bleaching agent as detergent. Let me quote you a quick example. Let's say Ariba is eating her favorite burger along with a lot of ketchup. Accidentally, a drop of ketchup falls on her white shirt. Now the whole white shirt is ruined because of a big, huge red stain. Now, in order to take that red stain off, and in order to take that color off, we're going to use a bleach. So what bleach is going to do, bleach is an oxidizing agent. It has an extra oxygen in its formula, which reacts with that red color and turns that red color as colorless. Wash it with the bleach, and you won't be able to even find a stain over there. There you go. The bleach did its work.
Yes, sir.
All right. You're still laughing about the favorite burger part, right? It's mouth-watering. Examples like these are always helpful for me. But don't go astray. Don't start thinking about the burger. Let's stick to chemistry. Actually, it's about time. So I think let's wind it up over